Welcome to this deep dive into OEIS A000233, Generalized Class Numbers. We're continuing our series for number theory students looking at the OEIS, and today we're tackling something that builds on, well, a really fundamental idea: class numbers. So, our mission today is to unpack what these generalized class numbers actually are, why do we need them, and how do they connect to bigger concepts like L functions and class field theory. We've got some notes from Milne, online discussions, the usual mix.
It's great to be here, yes. We're essentially climbing one level higher in abstraction from the basic class number. It's an idea that really unlocks a much richer view of number fields.
Okay, so let's start there, the foundation. When we just say class number, the usual one, what are we talking about? And how does that link to this OEIS sequence, A000233?
Right, so think back to Dedekind. Unique factorization of elements. It doesn't always hold in number rings, but ideals do factor uniquely. The class group essentially measures how far the ring is from having unique factorization of elements. It looks at ideals, modulo principal ideals.
And the class number is just the size of that group.
Exactly. It's the order of the class group, a really key invariant. Now, A000233 in OEIS, that lists the class numbers for fields like math BBQ, simple quadratic fields.
Okay.
But as you delve deeper, especially beyond these first examples, you find that this basic class number, well, it doesn't tell you everything you need to know.
Right. So if the standard class number gives us a snapshot, like you said, what drives the need for this wider angle, this generalization?
That's a good way to put it. The standard class number is perfect for understanding unramified abelian extensions. You know, extensions where prime ideals behave nicely. They don't split apart in complicated ways.
Okay, unramified.
But number theory is full of situations where primes do have more complex behavior upon extension. They ramify.
Oh.
And that's precisely where the generalized class number and the theory around it steps in. It gives us the machinery to handle ramification.
And that leads us to generalized class groups, defined with respect to a modulus dollar. That sounds like the key innovation here. What exactly is a modulus in this context?
Think of it like adding parameters to our measurement. The modulus dollars is a way to incorporate more refined information. It's formally an ideal M dollars combined with a set of real infinite primes,
So that can involve both the usual prime ideals and these infinite primes,
Yep.
the embedding.
Exactly. Mineralized class group, 7 in dollars, then considers ideals that are co-prime to in dollars, but the equivalence relation is stricter. Two ideals are equivalent if the ratio is principal, say generated by alpha, where alpha has to satisfy congruence conditions modulo in dollars and sign conditions at the real primes in infinity.
So alpha has to be like 1 modulo infinity.
Essentially, yes. Congruent to 1 modulo in dollars and positive at the specific real embeddings listed in infinity.
Okay, so choosing dollars lets us sort of zoom in on different aspects. Can you give an example or two of how Hilbert changes the group?
Sure. The simplest case, if you take the modulus win in dollar and f of t is empty, then $7 is just the ordinary ideal class group, our starting point.
Back to basics.
Right. Now, if you take $10 but include all real infinite primes in Levy 6, then $7 becomes the narrow class group.
Ah, the narrow class group. That distinguishes based on positivity.
Exactly. It cares if the generator of a principal ideal is totally positive or not. Finer information.
Okay.
And here's a nice concrete one. Take the base field cal, not the really, the rationals. Let the modulus just be 1 Malev dollar for some integer dollar, view as an ideal, and no infinite primes, so 1 Malev dollar. Then sec dollar is actually isomorphic to Mahler's dog.
Oh, the group of units modulo m. That's very tangible.
It is. It shows how this abstract definition connects back to something quite familiar from elementary number theory.
That's really neat. Okay, so these generalized groups, sec to dollar, their real power comes from class field theory, right? How does the main theorem adapt?
This is where it gets really powerful. The fundamental theorem of class field theory extends beautifully. It says that for any subgroup dollars you pick inside one of these generalized class groups, $2, there exists a unique abelian extension field dollar of your base field dollars. And this field is special. It's unramified outside the primes that divide the modulus dollars.
So Nairnals controls the allowed ramification.
Precisely. And the crucial link is that the norms of elements, or ideals, from dollars down to dollars, when viewed inside $2, form exactly the subgroup we started with. Although dollar is the class field for dollars, relative to dollar.
So every subgroup corresponds to a specific abelian extension whose ramification is constrained by dollars. How does the Hilbert class field fit into this picture? We know that's important.
The Hilbert class field is just a special case. It's the class field you get when you use the modulus not all dollars and take the trivial subgroup H within the usual class group C and dollar.
Okay, so $1 means no ramification allowed anywhere.
Exactly. That's why the Hilbert class field is the maximal unramified abelian extension of dollars, and its Galois group over dollars is isomorphic to the usual class group C alpha 1.
Like for math BBQ class number is 2, but the Hilbert class field is just math BBQ, which simplifies. Oh wait, Milne's example. Math BBQ class number 2, Hilbert class field is math BBQ quarter 1. I misspoke earlier.
Yes, math BBQ is the Hilbert class field, degree 2 over math BBQ, matching the class number. My apologies if I misspoke earlier about the units. The point is the Galois group matches the class group.
Got it. Okay, so Hilbert is the unramified story. Generalized class numbers, then, are really our ticket to understanding abelian extensions with ramification.
That's the key takeaway. By choosing a modulus dollar that includes the primes where we expect ramification, we can now describe and study those ramified abelian extensions using the corresponding group Siamal dollars. It opened up a whole new world of extensions to analyze.
In the Artin map, that's central to class field theory. How does it play with Siamal graph?
The Artin map is the bridge. It connects the arithmetic downstairs, in Tor specifically, prime ideals not dividing the conductor to automorphisms upstairs in the Galois group of an abelian extension L-collars. Now, if the conductor of L-collar divides our modulus dollar, the magic is that the Artin map, which initially takes ideals as input, actually factors through this generalized class group T dollars.
Meaning elements of C dollar correspond directly to Galois automorphism.
Yes. It gives a direct homomorphism from the generalized class group C dollars onto the Galois group Gal L-collar. It makes the connection very explicit.
Okay, wow. Finally, let's touch briefly on L functions. The sources hint at a deep connection there, too.
Oh, absolutely. It's not just algebra. There's deep analysis, too. For each character of a generalized class group C dollar dollars, that's a homomorphism, from C dollars to the complex numbers you can define in L-series.
Like Dirichlet L-series.
Exactly like Dirichlet L-series, if A math BBQ and gnome dollars. More generally, they're often called Hecke L-series or Weber L-series. These L-series generalize the Riemann zeta function and Dirichlet L functions. They encode incredibly detailed information about how prime ideals are distributed in the number field dollars, or rather, how they distribute among the classes in second dollars. The analytic properties of these L functions, like their zeros and poles, reflect the arithmetic structure captured by $3 and its associated class fields.
And this ties into even broader concepts.
Yes, as some discussions note, these Hecke L-series are special cases of Artin L functions associated with Galois representations, and in a much grander picture, automorphic L functions. Class field theory provides the analytic continuation and functional equation for these abelian L functions, which is foundational for the whole Langlands program, really.
So it's not just some abstract algebraic gadget. These generalized class numbers, they sit right at the intersection of field extensions, Galois theory, arithmetic statistics via L functions, all stemming from trying to understand number fields more deeply than the basic class number allows, like we see in OEIS A000233.
Precisely stated. They are fundamental. For any student wanting to grasp modern number theory, getting comfortable with generalized class groups and their role in class field theory is pretty essential. It's the gateway to understanding abelian extensions fully.
This has been incredibly illuminating. Thank you for guiding us through the intricacies of generalized class numbers. For all of you listening, especially those exploring number theory and the OEIS, and we hope this clarifies why we move beyond the standard class number. We definitely encourage you to dig deeper, look into how these class fields are actually constructed, explore the properties of these Hecke L characters in their L series. There's a vast and beautiful landscape there.